okay to use the hand mic instead, or is it supposed to be just a?
You can also use the hand mic if you want, I think.
Or is that okay? Or?
For me, it's fine. Yeah, if it will.
Can we use the hand mic?
Is this okay? I don't want to mess with the protocols. Unless you want to hear me like breathing a lot.
So you can either point here, right?
Yeah.
Or you do what Iñaki did.
Yeah, that's fine.
And maybe in the end, quickly repeat the question because you cannot hear it on the recording.
Oh, since I'm using this?
No, because you don't go around with the phone.
Okay.
With the microphone.
Okay.
Okay, so the next speaker is Jonathan Heckman. Higher symmetries by please.
Okay, thanks very much. And let me say thank you very much to the organizers for putting this together. I think we were all glad to be here after kind of 2 years, and hopefully there's no other horrible world events that delay the next one. Okay, so what I'll talk about is based on a few papers that appeared this year. So one is with Michele Del Zotto, Robert Moskroff, Shani Nadir-Manet, and Hao Zhang. Another one that recently appeared is with Miriam Svedic, Max Hubner, and Ethan Torres. And another one, which I'll only briefly mention, which will hopefully be out soon, is with Craig Laurie, Ling Lin, Hao Zhang, and Gianluca Zuccarotto. So let's see if I can remember everybody. So Robert, Hao, Ethan, and I think that's it. They're all getting their PhD soon, so look for them applying for postdocs soon. So and they all did a lot of the important work on this. Okay, so let me also mention a related paper which came out basically on the same day, related to some stuff I'll talk about later, that by Michele Del Zotto, Iñaki Garcia Extabarria, and Sakura Schaefer-Nemeki. And I'll also mention to look for Ling's talk later today, and Shani's poster in the poster session, and which will cover some aspects that I won't have time to really get into now. Okay, so let me begin with some motivation. So I think a general question one can ask is, what is quantum field theory? So there's a kind of a version that you teach in a kind of quantum field theory course based on writing down Lagrangians and so on. But we now have various examples coming from string theory that this may be a little bit too restrictive. And in particular, how should we be thinking about issues about quantum field theory at strong coupling? So examples, classic examples where it seems necessary to talk about string theory involve higher dimensional superconformal field theory. So still the kind of best evidence we have for the existence of things is all coming from string theory constructions of various kinds. And an important point is that the hallmark is that all of these examples, all of these fixed points are intrinsically strongly coupled. And so it's very hard to study them using Lagrangian methods. Okay, and then just to give some examples, so we have 60 CFTs. There's even a conjectural classification of these coming from F theory on elliptically fibered Calabi-Yau threefolds. X for me is always going to be some non-compact space. And the idea to build these is to take various curves, collapse them, and then there's D3 branes wrapped on those curves, giving you things like effective strings, which are becoming tensionless at the conformal fixed point. And a similar thing happens in terms of how we build 5D superconformal theories. You take an M theory on a Calabi-Yau threefold, and you can collapse, this should say, Y. You should collapse divisors in this space, and then if M5 branes wrap on this, again gives us tensionless strings. This is again the hallmark of having a fixed point. Okay, and then of course these are also useful for studying various strong coupling dynamics in lower dimensional theories by just compactifying what we have in 6 and 5, and conjecturally, perhaps it's true that you can make all the lower dimensional ones via this process, although the conjecture obviously has less and less evidence as you go down in dimension. Okay, so what are things you can compute? So suppose somebody hands you a list of these theories. What are things you might try to compute? One is the moduli space of vacua, like flat directions associated to operator vevs, scaling dimensions and correlation functions, and symmetries. And I'll be focusing on symmetries in part because they provide us a way of kind of constraining various other aspects of the theory. So for example, it can kind of dictate what we have in terms of the global form of the moduli space. It can constrain correlation functions. Okay. It constrains correlation functions, and in particular, also if we have, say, symmetries and we compute their anomalies or something like it, it can provide a very powerful constraint on possible renormalization group flows. So even if you don't have a Lagrangian, knowing something about the symmetries is kind of very core to understanding the defining properties of a given field theory. Okay, and so as Sakura already mentioned, generalized symmetries are kind of a very interesting way to kind of extend what we think we understand about such objects. And so it's kind of defining data, it is defining data of a quantum field theory, and it is important in kind of specifying what you mean by the actual theory, so it can resolve various ambiguities that can creep in otherwise. And so just to kind of set the terminology I'll use, zero forms act on local operators, one form symmetries act on line operators, and then you can have various kinds of higher groups that kind of entwine these things. I'll just focus on the simplest case of a two group in what follows, but basically the idea is that a lower dimensional zero form symmetry could, for example, act on the line operators of your theory. Okay, so Sakura already reviewed this, but I'll just be brief about it. So the idea is that if you had two line operators, for example, there could be a local operator in between. So you could think about this, for example, as like a Wilson line of a gauge theory, and then there could be a quark ending on it. And what we want to know is, can we change from, say, one type of Wilson line to another? So here's the quark, here's the Wilson line. And one of the things we want to understand is, for example, if I gave you an SUN gauge theory, do we want to talk about Wilson lines being in, say, the fundamental representation or not? Do we allow this? And so we know that if you had, say, gauge theory with group SUN mod ZN, then we're not allowed to talk about Wilson line in the fundamental, but still we can talk about them in real representations. So it's this kind of important question about what is the global structure of the possible extended objects that we'd like to get at. Now, there's this topological interpretation, which again, Sakura nicely reviewed. We have these local operators, and you can think of like a Gauss's law for like counting the flux associated with that thing that surrounds the local operator. So it's a codimension 1 object. I'll write that as some script u d minus 1. And then for line operators, it's a codimension d minus 2. And then each one of these little things here is associated with one of these topological operators. And there's these walls, they intersect one another. And so one of the things you can ask about is, if I kind of do the analog of a crossing relation between these different codimension objects, is it equal to itself? And the failure of associativity is kind of the hallmark of having one of these two-group structures. So you'll see that I kind of slid it around like this. This might be familiar to you that know about, say, things like string field theory, things like this. There's a kind of failure of associativity, and it's captured by this kind of triple involving the group generators we have over here. Okay, so so again, a little bit of this was reviewed in Sakura, but just to kind of set the notation and formalism, the way we can kind of capture the effects of, say, starting with a particular class of line operators and whether things got screened out is in terms of a collection of short exact sequences or a particular long exact sequence. So here I have the one associated with the zero form symmetry. Remember, that's the one associated to acting on local operators. And so G tilde is going to be what I'll refer to as the naive group. So in other words, it's going to be the group where we just, for example, take SUN rather than SUN modded out by, say, a center or something like this. And then there can be a quotienting. So for exact sequences, remember the idea is you take this thing here and divide by this thing here to tell you what this thing here is. So there could be a non-trivial quotient by some subgroup, it's in the center of G tilde, to give us the actual group G. And likewise, we can do a similar thing talking about, say, a naive one-form symmetry, and then one that might have some screening effect. And it turns out that you have to put the quotient like this. So A is going to be the true one-form symmetry. G0 is the true zero-form symmetry. And these two, just using statements about putting together such short exact sequences, can all be combined into a particular long exact sequence. And the statement of having, for example, a two-group is that this thing does not split. So in other words, the summands, so the quotients don't just like come as like sums, direct sums. There's an actual non-trivial quotient gluing things together. Okay, so here's the main claim for this part. So the idea is that actually all of these terms can actually be read off directly from the geometry. So what I'm going to do is explain how you read these things directly from the geometry. And so a lot of the previous work in this direction has involved kind of various pieces from field theory, very nice work from field theory, and also various kind of guesses about what's going on when you start pushing things into a strong coupling. So what I'm going to tell you about is really the part associated with the center. So remember I had G tilde here and G. Now I'll just talk about the center. That's the part we will actually detect via geometry. And so my goal is going to be to basically tell you where each of these terms comes from in the context of geometry. Okay, and my main focus is going to be on various kinds of gluing constructions for orbifolds. So in the paper with Miriam, Max, and Ethan, we basically did a bunch of different examples. One of them is 5D CFTs, was already mentioned actually in a question by Kamran, involving various kind of finite subgroups of SU3, quotienting C3. This provides a large class of 5D CFTs, and I'll explain what we understand about how to compute in those examples. There's other examples we considered, for example, 6D CFTs, compactified. I won't talk too much about this, but I'll mention some of the results. And also M-theory on local G2. We can use kind of very similar techniques. So these two are more related to 5D and 6D, if you like, and this one is more in the context of four-dimensional theories. Okay, so to get going, first let me briefly talk about how we're going to try and engineer things like higher symmetries from the context from a geometric starting point. Okay, so to begin, I'll just kind of go by way of example. Kind of the first paper, I think, that kind of did this in the context of finding, higher symmetries. We didn't say it in exactly those terms, but basically, main idea is to take like a 6D CFT. How do we engineer this in F-theory? This here is the two-dimensional complex base of the model. Each one of these circles is a curve, a P1. And to build basically a defect in the system, you take the non-compact cycle, so 6, 7 directions are for the compact direction. We take the 8, 9 directions, and we consider a wrapped D3 ring going out basically to infinity. So here, the star here is kind of the singularity. After crushing all of the S2s to 0 size, we have this defect extending out, and then that is a thing that will look like a non-dynamical string in the 6-dimensional field theory. So you can see, because it fills the 0 and 1 directions. And it's non-dynamical because the volume that it wraps is infinite in size. Okay, so what is the defect group? It's basically a way of asking about what's been screened by dynamical objects. So a dynamical string would have come from taking the 6, 7 directions, wrapping a D3 burn on that, and then the pieces which cannot be screened is basically provided by an appropriate quotient. And I'll be a little bit more precise on the next slide. So more generally, the idea is that we basically do the same game in any kind of string construction with all the branes that we have, and we look for objects that kind of go from the singularity all the way out to the boundary. And this is captured by various kinds of quotients involving basically chains that are allowed to end on the boundary, modulo compact cycles. And then whatever the branes you have in your particular example are, that tells you the kind of spectrum of at least supersymmetric objects that we're allowed to speak about. Okay. And here's just another picture. So the idea is that we again have this brane wrapping out, and then it does something over at the boundary. So this is kind of the extended object. And what we're doing is performing this quotient to tell us about the things that could not be screened by things localized directly at the singularity. So basically, the name of the game for getting the higher symmetries is to calculate these kinds of quotients. Okay, so what are the higher symmetries? So defects, like point operators, that's not really a defect, but like a line operator, surface operator, things like this, they're acted upon by the various symmetries. And so what we have to do is kind of split this defect group, into an electric and magnetic piece. This is similar to how in quantum mechanics we have to choose a collection of position and momentum variables. We have to pick some that can simultaneously all commute with one another. That's the analog of specifying polarization. And it's given by this dual group. So I'll do all my Pontryagin duals by checks. So homology cycles and things like that are going to be associated with the actual defect. And then the thing that we use, the group that acts on those, is going to be this dual thing, this check. Okay, and there's many, many papers talking about various aspects of this. But that is the main idea. Okay, so let me begin by asking what can we calculate in the context of 5D CFTs and these non-abelian orbifolds. Okay, so we'd like to calculate this. Now, historically, one of the main methods that was used prior to our work was basically say, well, I'm going to write down a singularity, and then I'll perform the explicit blowups and resolutions. Now, you can, of course, do this in example by example, but the question is whether that's kind of computationally practical to do in many cases and whether it kind of obscures some of the physics. And so what I'll do is kind of provide you with a way of doing this that does not require any resolutions of the singularity. And there's two kinds of things we could talk about, the electric 1 form and the magnetic 2 form in this case. And they have a non-trivial pairing with each other because we're in 5 dimensions now. So I'll focus on the electric one. There's an analogous story you can work out quite quickly for the magnetic 2 form symmetry, but for interest of time and because it's almost redundant in this case, I'll focus on this one. Okay, so how are we going to calculate this? So here's going to be my non-compact Calabi-Yau. This is making my 5D CFT. The boundary is given by a 5-sphere. There's a group action, and the reason I get this on, remember the S5 has some SO6 symmetry acting upon it. SU3 embeds inside of SO6 or SU4. And so we have a non-trivial group action on the boundary 5-sphere. And what we'd like to know about is what's going on in terms of this calculation. Can we calculate this quotient in this particular case? And notice, by the way, that the quotient space could itself have various kinds of fixed point loci. So we're allowing for that possibility. That does generically happen in many cases, but we need to be able to calculate this kind of quotient in full generality. Okay, so there's two approaches that we kind of developed to do this. One is via quivers, and physically you should think about this as taking the 5D CFT, compactifying on a circle, and then looking at the spectrum of BPS particles, probing the orbifold singularity. From this, you get a quiver representation, and essentially from the torsion of the co-kernel of the adjacency matrix, you can read off the electric and magnetic symmetries for the 5D theory. So I'm not going to talk about that too much well, I'm not going to talk about it today. It also works for non-orbifold cases. I'll refer you to Shani's poster later today for more details on that approach. What I'll focus on today, because it will fit with the kind of other pieces, is to focus on an approach based on algebraic topology, where we just read it directly from the fundamental group of the quotiented 5-sphere. Okay, so it's basically like a couple of lines to read off the result in this way, which is kind of nice. What we need is to calculate H1 of this boundary space. One can figure this out from the relative homology sequence, long exact sequence. And H1 itself is just the abelianization of the fundamental group. So what I need to do is tell you about how to calculate just the fundamental group and its abelianization. So abelianization for me just means take all the elements and then impose additional relations so that everybody commutes. So abelianization in particular is always abelian. Okay, here is the theorem we're going to use. It's an old theorem. The point is that this thing here is given by gamma mod n. What is n? N is a normal subgroup of gamma that is generated by looking for fixed points under the group action on the 5-sphere. So it could a priori happen that there's some fixed points. Now, if there are no fixed points, then this is the case you probably know best from, say, lens spaces or free group actions. Then you'll just get gamma. But there could be some fixed points, and we need the quotient by that stuff. The claim is that this is our fundamental group. And so we now have this. So this is the answer for all of the electric one-form symmetries. It fits on one line, and it follows from this very old theorem from Armstrong. Now, what is the physics associated with the things that were fixed? In many cases, these can be interpreted as flavor branes. So in other words, 6 branes, they carry flavor symmetries, and they're important for telling us more about what is going on in the corresponding field theories. For example, the flavor symmetries, the zero-form symmetries, and, as we might expect, they're going to mix in a non-trivial way with the one-form symmetry. So now what I need to do is tell you more about what is going on with these fixed point loci and what is the physics associated to those. Okay, so here is a simple example. A Z-n orbifold, I guess. So if you set n equals, 3, then you'll just have omega, omega, omega. And the point is that for n odd, there's no fixed point locus. And for n even, there is a fixed point locus. It's a Z2 subgroup, or it's a Z2 finite group. And the locus can be seen quite simply by looking at Z1 and Z2 set to 0. So what do we get for the higher form symmetry? You get Z mod n if n is odd, and Z mod n divided by 2 if n is even. Here's another example that has a trivial one-form symmetry. In this case, the fixed point locus is so big that basically quotienting by it kind of destroys all the possible one-form symmetry. So this, I'll come back to this example. This is this engineers for you the 5D TN theories. And doing this agrees with kind of other methods based on kind of doing explicit toric geometry methods and blowups. Okay, so the general idea is that as the orbit of gamma increases, so does the fixed point locus, and that usually kind of tends to limit and constrain and lower the amount of higher form symmetry you can have. But not always. I mean, we can also write down infinite families that retain it as you kind of increase the order of gamma. Okay, so now let me get back to flavor branes. So we have our CFT, or quantum field theory, supersymmetric quantum field theory, and we have this cone-like structure. So there's the boundary out here, and then there could be a flavor brane, some fixed point locus that extends all the way from here out to the boundary space del x. And I'll refer to kind of the location of where this flavor brain kind of intersects at the boundary as k. I guess k for not, or something like this. It's usually going to be a one cycle in the cases I'll talk about. But k is just where this flavor brain comes in and intersects. Why am I calling this a flavor brain? Here's the point. It often looks like an ADE singularity. So C2 mod gamma. And this, as we know, gives you engineers a 7-dimensional super Yang-Mills theory. And the ADE type of that finite group of SU2 dictates the corresponding Lie algebra that we have. But this does not directly tell you the global form of the flavor symmetry. And so part of the task here is to tell you, okay, is it SUN or is it SUN mod ZN? Is it E6 or is it E6 mod Z3? This is the kind of thing we would like to be able to answer in order to tell us what is going on with the zero-form symmetry, the one-form symmetry, and so on. Let me mention or advertise something that is going to appear soon and will also feature in Ling's talk in some form, I think, which is that actually, if you take into account things like the R symmetry and also the space-time symmetry, there can be a non-trivial quotient across not just the flavor symmetries, but also the R symmetry and the space-time Lorentz group. So this is a subtlety. Spotting the R symmetries and these kind of constructions is a little bit hard, but using kind of bottom-up methods, we can kind of detect it quite easily. Well, easily. We can detect it. And the point is that this quotient thing that I'll tell you about actually receives some further correction. So look for Ling's talk for more details on that. OK, so now what I'm going to do is tell you about how to read off the zero-form and the one-form symmetries in these examples. OK, so here's the idea. We have X, and we have some boundary geometry. And what we're going to do is take, if you like, we're going to fatten up the region where the flavor brain is. It's some tubular neighborhood. T is for tubular. And we're going to fatten up some region. And what we're going to ask about is if we take X and delete K, I'll call that partial X circ. So that's just deleting K. And I want to compare that to what happens if I cut out this kind of fattened up region, T of K. And so this can be thought of as kind of looking at the boundary of the boundary. So we've cut something out of the boundary, and we're going to be asking about that boundary geometry itself. Now, since we're talking about boundaries of boundaries and things like this, it's going to be dictated by this long exact sequence by Meyer and Vitoris from a while ago. So the idea is that we kind of look at this intersection between partial X circ intersected with the tubular neighborhood of where those flavor brains are. And then it has a sequence as cutting it up into these individual pieces where we look at the homology pieces individually. And then we start gluing it back together. And the thing continues where you just kind of start shifting the degrees in the singular homology. So remember that partial x0 just involves deleting k, so there is a non-trivial intersection between partial x circ and tk. OK, so basically the idea is that the long exact sequence that we have for that 2 group is going to follow from the long exact sequence of Meyer-Vitoris. So what I'm going to do is say, take this Meyer-Vitoris sequence and then start interpreting the different elements as telling me about the short exact sequences for the zero-form and one-form symmetry and how it combines into the long exact sequence for the 2 group. So I'll go through in stages. I'll talk about zero-form symmetry first via flavor brains. So I'll neglect like other possible accidental things that you can't see through the flavor brains or non-trivial isometries. Those will not be part of my discussion. Then I'll move on to the one-form symmetry and then how they get entwined through the 2 group. Now the one-form symmetry part we actually already did. And so the point is that now I'll focus on this and see how it fits with this. OK, zero-form symmetry. How are we going to read this off? So here's the naive answer. I just told you that the flavor brain looks like C2 mod gamma. Now if I go to the boundary of the boundary, what is the boundary of C2 mod gamma? Well, it's a 3-sphere mod by gamma. OK? So this is giving us our kind of boundary, generalized lens space, if you like. And the naive answer is just that this thing is simply connected. So it's the one where we don't quotient by anything in the center of the group. But are we talking about SUN, or could it really be that G might be something else, like we quotient by the center? So again, an example is SUN versus SUN mod ZN, or say E6 versus E6 mod Z3. Which of these is the correct answer for the zero-form symmetry? How can we read this from the geometry? OK, so what is the answer here? Well, this thing here is just dictated by taking the pi1, sorry, the abelianization of pi1 of this thing. So the center of the naive flavor symmetry is just the Pontryagin dual of the abelianization of gamma. The check there is just to remind me that sometimes I'm talking about cycles and sometimes I'm talking about the group acting upon the cycles. But the point is that it's just the abelianization of gamma. So for example, from this you would read off that SUN has a ZN center, and for E6 it's a similar thing. The abelianization of the E6 finite subgroup is Z3. And so if we have multiple factors, we just sum them up. So this I is running over all the different components of the flavor brane loci. So there could be more than one flavor 6 brane located in the boundary geometry. We just sum over all of them. And this is our answer for the naive center of the thing. What's the actual zero form symmetry? Well, to read that off, I have to tell you where I got my line operators from in the first place. Where are they coming from? They're coming from M2 branes. And so they stretch out. So there's one spatial direction here. Then there's also some line, it's cutting out some one cycle on the boundary. And then in the space-time itself, remember there's still the time direction. That's like a heavy quark, the world line of that heavy quark. That's our Wilson line, like that. Now, this one is a little bit hard for me to do in a couple of minutes, but the point is that there's, again, a screening mechanism in play. And from the Meyer-Vittoris sequence, so hopefully you remember a little bit about it, from what I said, there's this projection of H1, or this embedding of H1 del X circ into TK into the H1 associated with the tubular neighborhoods, taking the kernel of that map and then taking this thing here and quotienting by it, tells us what we're actually screening by in the corresponding flavor symmetry. So what is the actual center that we're dealing with? It's ZG tilde modulo C. And the idea is something where we take the M2 branes at the boundary and we say, well, how can we pass one of them from one flavor stack to a different one? It's precisely captured by whether this gluing that we use in Meyer-Vittoris is non-trivial or not. Okay, so that's the zero form symmetry. How about the one form symmetry? So let me again refer you back to Meyer-Vittoris, which I'm sure you've all memorized by now, which is this complicated thing here. So now we're going to talk about K equals going up in degree to talk about the one form symmetry. Here's what we get. Oh, this is a typo. This should be del xk. All we have to do is look at this thing minus k. And what we do is we start looking at, for the naive one form symmetry, just h1 of del x0. Now remember, the thing that's on the boundary is not del x0. It's actually all of del x. What we've done here is we've deleted all the locations where the flavor branes are. And so we're going to get a different answer from what the actual one form symmetry is. How do I know it's different? Because I already told you how to calculate that in some examples. That was given by h1 of partial x, not the thing with the tubular neighborhoods, or sorry, the k's cut out. So remember what I told you. This thing here is this electric one form symmetry. That's calculated by h1 of partial x, no circ, or anything like that. So we had this part where we cut out the boundary of the boundary, this thing here. And now I put it back in and I've taken it back out. So that's accounting for the naive one form symmetry versus the actual one. Now, the two group symmetry, okay, let me go on. So that's the zero form and one form symmetry. Now let me go on to two group symmetry. So again, here's our long exact sequence. All I'm going to do is take those pieces and start sticking them together to form two different short exact sequences and one long exact sequence. Here's the claim. So just remember, this is the claim about what you're looking for in a two-group structure. Here I'm going to take the center of the naive zero-form symmetry, the center of the actual one, the naive one-form symmetry, and the actual one-form symmetry. This is the long exact sequence. There's a non-trivial extension if I have this so-called Bockstein map where the coefficients switch from the quotienting action, this C, into here. This BG here is just the classifying space for the group. And here's what we get. So each of these terms has now been embedded into something involving the geometry. So what am I doing here? This is the one we already talked about at the very beginning, where we said we're going to read this off from H1 of the boundary space. Again, checks and so on. The naive one is where I cut out all the flavor branes. And then I talk about the center. Okay, that's this thing here. That's the naive one, where I just say cut out the flavor branes and just study their individual lens spaces. And then this is the part which is, if you like, the most challenging, where you say, oh, well, actually, it's getting quotiented by something. But that quotient is precisely dictated. That's the point I want to stress. It's precisely dictated by Meyer-Vittoris. So there's, so just falling into your lap from that description. Okay, so now let me revisit the non-abelian orbifolds examples that I already mentioned. So I'll mainly focus on the abelian ones, although we can basically clean out the story also for non-abelian ones, as I'll mention too. Okay, so here is the main idea. Let me first focus, or my main focus will be on the case where this is an abelian group. So in this case, I have two choices. One is it's either z mod some integers, or z mod n times z mod m, so a product of two cyclic groups. Okay, so what does the boundary C3 look like? Well, C3 itself is a toric space, and so what I can do is I can just ask what's happening at the boundary. Turns out that it's just some T3 fibration over a two-dimensional base, and here's my picture of the base. It's just some triangle, so delta. And what we're doing when we take the finite group is we're just basically acting upon the T3 fibers. And so what's happening is that, remember in the toric geometry picture, as you start hitting the boundaries, various circles will start to degenerate in various ways. What is happening here? We'll still have that degeneration, but we're subject to not really having T3 in the same way. It'll be T3 mod this finite group gamma. Okay, so here's the SUN gauge theory example at level n. There's basically, this red thing here is like basically what the smooth part deformation retracts onto. So all we have to do is calculate with respect to this thing here and various fixed loci. So what do you get? Remember there was this fixed point locus for this Z2 symmetry. That naively gives us an SU2 because it's C2 mod Z2. We know that that engineers an SU2 gauge theory. Now, if you go through the computation of what the A tilde, and so on is, what you find is that there's a non-trivial quotient by this Z2. So we wind up with SO3 rather than SU2. And that agrees with what other folks found using kind of combinations of geometry plus gauge theory methods. Okay. Here it is just again. Here's the exact sequence I was talking about. So in this particular case, we get this thing here. And so there's no center, of course, for this one here after I do my quotient. And then you can do a similar thing where you just read off from the pi 1 and how it fits together for what the naive one-form symmetry is and what the actual one is. There's a non-trivial extension in this case if n itself is even. And so in this case, it doesn't just split like this. Okay. Here's the Tn theory. This one has, if you like, a boring one-form symmetry. So it has no two-group in particular. But it has an interesting zero-form symmetry. And so for n not equal to 3, we can kind of read off from the geometry where the various flavor loci are. There's 3 of them. Here's, again, the deformation retraction picture in that red thing here. And we have these orbifold group actions like this. The naive answer is just SUN cubed. And you can quotient by, it turns out there's a Zn cross Zn that you're now quotienting by. So that is the global form of the zero-form symmetry in this case. For n equals 3, what you can spot is an SU3 cubed mod Z3 squared. So if you take into account the enhancement that's known to take place in E6, you'd be actually expecting from this an E6 mod Z3. And that agrees with some statements that appeared in this for 4D Tn theory. Although there are some subtleties related to this, in particular having to do with possible mixings with R symmetry, but let me not get into that right now. But that is, that's our answer for 5D Tn. And you can generalize it. So here let me just go all the way to the most general non-abelian case. So using orbifold homology, what you can do is you can actually read off all of the answers in one shot. And so using orbifold homology, it turns out that the answer for this group is just the abelianization of that finite group gamma that I mentioned. And then this one I already told you about is the one-form symmetry. That's this ab gamma mod n. And then there's kind of the twisted part left over, which is defined implicitly by this, this exact sequence. And so this was kind of put forward conjecturally in this earlier paper. And then I guess a month or two later, we kind of firmed it up as demonstrating that this was actually true. So all of that follows in one shot. And if you like, all of the C3 mod gammas can be analyzed in pretty direct terms just using these statements. Okay, let me turn to a few more examples, but I'll basically be very quick with these in interest of time and also appetite for lunch. Okay, so 6D conformal matter on a circle. So there's many, I'm sorry if I've missed any references. the idea is basically all of these 60 CFTs basically just look like generalized quivers. And so you could ask, what is the global zero form symmetry in these cases, and the one form symmetry? So what we can do is using exactly the same cutting and gluing techniques, where in this case, you do cutting and gluing both in terms of the only subtlety is whether the elliptic fibration changes anything relative to what we had in the orbifold group action. The main statement is, no, it doesn't. I mean, there's some technicalities with that, but not really. And so from the exact same statements about orbifolds, we can read off now the global form of the zero form symmetry. In the case I'm mentioning, all of the gauge groups here are basically the same, and so you just get a G left times a G right modulo this kind of a diagonal center. And in some of these cases, it just looks like it's trivial. There are other cases where it is non-trivial, so I don't want to give the impression that it's always trivial. But the point is that you can, again, read this off directly from the corresponding geometry. And then in Ling's talk, there will be some further mention of how to do this from a complementary method using kind of a bottom-up approach, just looking at kind of the associated gauge theory you get on the tensor branch of the CFT. And OK, that's basically the answer for these 60 theories on a circle. You can do a similar thing for SQCD-like theories on local G2 constructions, local G2 spaces. Now, what do I mean by that? Isn't it a very challenging problem to get SQCD-like theories from G2? Metrically, yes. Topologically, not so much. So the point is that we don't even care too much about what's going on in the interior, just the existence of a possible brane construction lifting to a local G2. So we can use some results that were already developed for SQCD-like theories involving D6 branes, for example, on local Calabi-Yau threefolds and 2A constructions. These can all be lifted to G2 at the level of topology at the boundary. And for example, we can use this to study, for example, spin 2NC gauge theory with an SUNF mod Z2 flavor group. And for example, we can also study whether there's a 2 group in this case. And indeed, it does agree with what they had there. We can just read this directly from the geometry. This one is actually a little bit more subtle. It's actually the one we were working on the most initially. It's a little bit more subtle, in particular because kind of the one-form symmetry, there's an electric one-form symmetry and a magnetic one-form symmetry. And so keeping those straight is also part of the challenge. OK, so let me now wrap up and summarize some future directions. So what did I tell you about? I told you about zero form, one form, and 2 groups via geometry. And my main focus was on glued orbifolds, although hopefully you can see that it extends in various directions beyond that, some of which we're working on now. It's known that, so what is to be done in the future? I've just listed a couple examples, but there's many more to consider. It's known that if you consider kind of the boundary behavior of various kinds of fractional fluxes, that it can change the global structure of the symmetry group that you have. How do we read that off in this kind of gluing construction that I mentioned? What is the physics of the 2 groups, in particular for these 5D and 6D theories? And another very interesting question is, OK, what happens if we start putting these things inside of compact models? We already have some examples where we can study this, and hopefully that will be done relatively soon. But the point is that there are models where you can kind of ask, what happens if we compactify at the level of, taking a general quantum field theory, you might ask, can you couple it to gravity? That's a very natural question. What happens to all of these higher structures in those limits? Do they just completely, in many cases they trivialize, but the way in which they trivialize is the interesting part. So anyway, I'll stop there. So thanks for your attention, and that's it.
Thank you very much, Jonathan. Are there any questions? Yes. If you can briefly, for the recording.
Yes. OK, so Ling's question was in terms of, we have this Bockstein map that usually is just stated in purely field theoretic terms. And the point is that what we do is we have some map from a cohomology class here, BG, the classifying space here, with coefficients in that quotienting group C, into H3 of classifying space of this with respect to the one-form symmetry coefficients. And the question was, OK, great. Can you actually see that from geometry? So at some level, I believe the answer is yes. But the answer, at least for my purposes, is that I don't actually need to know that in order to proceed. The point is, the key point is that this thing, this trick with the Bochstein map, is a way to kind of guarantee that your extension is not split. But at a practical level, if you say, I don't care about Bochstein, whatever, this or that, what would the geometry actually tell me? Well, all I really need to do is just take in a given exact sequence and just verify directly whether the thing is splitting or not. That's operationally like what I need to do. Now, of course, it's very useful to have this Bochstein map around. And I believe that there's, well, if you like it implicitly, it's encoded in Meyer-Vittorius in some kind of generalized notion of cohomology you might want to talk about. But the point is that it's not directly necessary for reading this off. Tunings. Well, the thing I would tune is some kind of discrete parameter in many cases, so I don't know if that counts as a tuning. So for example, let's see, I have an example. Here. So this is for the C3 mod Z2n. And so if n is even versus n is odd, sometimes you'll get a 2 group and sometimes you won't. Tuning by a continuous modulus? Let me think about that. I think the answer actually is yes, but it would look like a very sharp singular transition. So for example, I can trivialize all these, a lot of these one-form symmetries by just sticking it inside of a compact model, right? And then all the interesting physics will happen if I decouple and I go to some singular limit, right? So that if you like, that's a tuning that I could do, but it's a very abrupt transition. It's basically saying, like, in the deep infrared, after I've completely decoupled gravity, then I expect something like the one-form symmetry to emerge. And then depending on, so that would be an example where you can kind of like force it to happen and that, in fact, that's how we get it in all these examples, right? We're visualizing in terms of some non-compact thing, and if you tried to compactify, if it is possible to compactify it, then in many cases it'll just trivialize. Yeah. Higgs branch. For any of these theories or what? What do I expect to happen? Well, to answer that question, I think actually I have to be a little bit careful because I think I first have to analyze what's going on with the global form of the R symmetry in these models before I get into discussing the Higgs branch physics. So the short answer is I haven't thought about it, but I think the preliminary question is actually to make sure that things having to do with the global R symmetry are properly taken into account in this setting. As Ling will mention, so I'm gonna, there is this kind of non-trivial effect from a quotient that extends not just on the global flavor symmetries, but also into the R symmetry. And this is actually pretty important because if you just read things straight from the superconformal index, you can potentially get a misleading answer for the global form of the zero form symmetry because there's particular projections you do on the R symmetry states. And so when somebody tells you, oh yes, the Minahan-Nemeschansky theory has global symmetry E6 mod Z3, there's a sense in which it's neglecting things having to do with the R symmetry. Now this is especially important in the context of what's going on with the Higgs branch, because on the Higgs branch, we break the R symmetry. And so to answer your question, I think I first have to answer this preliminary question. And so if you pressed me on this SUNN model, I'd be willing to bet, I don't know how much, that the answer is that the Z2 R symmetry does come in and quotients the whole thing. So it's really like an SU2 flavor times an SU2 R symmetry and then modding by a common Z2. That would be my guess, but we haven't, I think, directly checked it. And so